Yeah, welcome to this talk. I will be talking about the paper Arithmetic Circuit Implementations of S-Boxes for SKINNY and PHOTON in MPC. And this is joint work with Aisajan and Bart. So the title has two components, MPC and SKINNY and PHOTON. So first I will quickly introduce MPC. So MPC is secure multi-party computation, and it's a family of protocols where multiple parties can jointly compute a function on private inputs. So, so here in this example, we have party 1 who has input x and party 2 who has input y, and they want to compute f of x and y. And in MPC, you can compute this function such that the other parties don't learn the private inputs. So P1 doesn't learn y and P2 doesn't learn x. And during this computation, you might represent your function using, for instance, XOR gates or linear operations in some arithmetic, and this is usually cheap to do. But if you use nonlinear operation in your function, such as AND gates or multiplication, then this is costly. So therefore, there is some, you want to represent your function that you want to compute in a way that avoids these costly operations. And during this computation, the parties will work on secret shares of values. And secret shares I will denote with this double bracket notation. And in the end, the parties get a share of the output, and then they can reconstruct this if they want. And now the second part, we are evaluating in this paper the tweakable block cipher SKINNY and the permutation photon in MPC. So now I want to convince you that this has some interesting applications. So for instance, what we can do is we can build oblivious PRFs using this. So in an oblivious PRF, one party provides the input to the PRF and gets the output, and the other party provides the evaluation key. And as in MPC, what you also want is that the party who provides the evaluation key doesn't learn the input-output pair, and the party who provides the input should not learn the evaluation key. So this is also, and now using a block cipher here for the PRF or another symmetric key primitive and evaluating this in an MPC protocol achieves exactly this. What you can also do is you can build a more privacy-preserving data processing pipeline using this. Here you have a client who has data that is encrypted under symmetric key, and you have servers who have shares of this symmetric key. And then the servers, once they receive the data, they can decrypt the data in MPC, and then they do the processing, for instance, using machine learning to infer some interesting properties. And in the end, you can encrypt it again and send it back to the client. What you can also do is you can build signatures. In this case, you can build signatures using a zero-knowledge proof, for instance, using the MPC in the head approach for this. So in this, Alice wants to create a signature, and her signing key is the symmetric key of the PRF. And Bob receives, or Bob wants to check the signature, and the public key of this is an evaluation pair. And then Alice can run an MPC in the head zero-knowledge proof, where she, in a simplified way, she simulates an MPC protocol of, for instance, 5 players who compute this evaluation pair. And then she records the transcripts of a subset of these players, and this constitutes the signature. And then to check the signature, Bob would check whether the views of these parties are consistent in the protocol. So in previous works, some people already have studied program representations of symmetric key primitives in MPC. So there is this work by Mandal and Gong, who studied all the NIST lightweight crypto, all the round 2 primitives for the NIST lightweight competition, but they only studied the Boolean circuit of these primitives. Then there's also a line of work that implements AES using a general purpose MPC protocol in an arithmetic circuit. And then there's also the work of Damgard and Zacharias who are designing a specific MPC protocol just to evaluate AES. And in our work, we are looking at the tweakable block cipher SKINNY and the permutation photon, and we will express them in arithmetic circuits in binary fields of 4 bits and 8 bits. And we're also using a general purpose MPC protocol to evaluate this. So, and now if we want to, so all these, or many of these primitives, they share a common structure because they follow the substitution permutation network approach. And in this approach, or in this structure, you have a state of cells, like a matrix of cells, and this matrix and this state is iteratively changed using a round function, and the round function always applies the same steps in order. And what I have put here on the slide is the round function of SKINNY. And in the talk, I will concentrate on SKINNY only, and only on the SKINNY version that uses 4-bit S boxes. And in SKINNY, so the state is a 4x4 matrix of cells, and these are first to each of the cells. In the first step, to each of the cells, the S box is applied. The S box is a nonlinear substitution function, and you can see the mapping in the table there. Afterwards, round constants are added, and the round key is added as well. Then the positions of the cells in the matrix are rotated, and afterwards the state is multiplied with a public matrix M. And now if we assume that in our MPC evaluation the state X will be secret and the round key will be a secret shared because it comes from the key that is secret, then we can see that the last 3 operations are linear operations because they only involve linear operations with respect to the secret shares. And then this means that we only have to concentrate on the S box and how to implement this. This is what, and I will show you our approach for 4-bit S boxes. But first, let's set up a baseline. The baseline would be to emulate the Boolean representation of the primitive that we already know from previous works. And in this representation, the cell consists of four shares, and each share holds one bit of the state. And then we can compute the S box using the formula that we would use for a hardware implementation of SKINNY, which I put here. And this S box costs 4 AND gates to compute. And also the other steps, so the round Twiki addition and mixed column layer is free, cheap, because it's a linear operation. So in total, this means that for the 16 S boxes that I apply every round and the 4 AND gates, and for all the rounds, in the end, the cost to evaluate SKINNY is this number of multiplications. And then if we now look and start to make this more arithmetic, the first step is we group the bits from each cell into only one share. And we want to do this grouping such that all the operations except the S box remain linear operations. So this means that the cell is now one share, and we encode it in this polynomial here. And then we can compute the S box in a clever way using a polynomial decomposition of the interpolating polynomial. And the linear parts of the primitive remain linear. So the formula on the right requires 2 multiplications to evaluate, and it requires 8 random bits from the preprocessing. So this means that for the cost, we already have halved the number of multiplications that you need to compute SKINNY. And what I will show you now is how we can find coefficients for P0, Q0, and P1. And for this, we're using the polynomial decomposition from Coron, Roy, and Vivek. So, and this decomposition works by interpolating the polynomial first in the 4-bit field. So the polynomial that you see here is the skinny forward S-box for 4 bits. And then we decompose it into the form that you saw earlier, where we require that P and Q only contain certain monomials. Ideally, we would like them to contain only squares. So z cubed, z to the 4, and z to the 8. And now if we want to solve this for coefficients, we see that this is a nonlinear equation. So what we can do is we can set random coefficients for Q0 and then hope that we can solve now this linear system for the coefficients of the P polynomials. However, for the 4-bit case, unfortunately, we don't find a solution for this. So the next best thing we can do is we can add powers of 3 to the monomials. And for this, we can find solutions. We can not only for this particular decomposition, but for any decomposition of 4-bit to 4-bit functions. So what remains to do now in MPC is to compute these monomials. And we will compute them using a property of the binary field, where squaring in this field is a bit linear operation. So this means when we first bit decompose our share, meaning that we have one share that encodes the bits in this polynomial, and then we turn this into 4 shares that each hold the bit in the constant coefficient of the polynomial. Then we can express squaring using a simple matrix multiplication. So this means that the coefficients B0 prime to B3 prime, if you combine them again into the polynomial, then you get z squared. And of course, you can do the same then by another matrix multiplication to get z to the 4 and z to the 8. And now, since this alone does not compute all the powers we need to compute z cubed using the normal MPC multiplication. And then we can do the same trick. So we bit decompose this value, and then we can repeat the free squaring to get z to the 6, z to the 12, and z to the 9 is z to the 24 mod 15. It wraps around in the exponent. So we implemented this in a 3-party setting using Mascot. Mascot is a dishonest, majority, maliciously secure MPC protocol. And this shows an evaluation of Skinny 64.128. So 64 bits block size in 128-bit tweaky. The entry on top, the blue entry, is the baseline. This would be the Boolean circuit. And our polynomial decomposition is in the bottom left. And I forgot to. So we measure the total execution time, and we measure the total time the total data each player sends. And then what we get is we find that the polynomial decomposition uses roughly 50% less data and is 18% faster in an execution. You also see that there is another implementation approach that we have in the paper called SQ4, which is the direct evaluation of the interpolating polynomial using more squaring tricks. You see that this approach is slower than the baseline, but it still uses or sends less data. But for this, you have to check the full paper. Then, so to conclude, in this paper we have, or we show that if you use a polynomial decomposition, you can improve the evaluation of any 4-bit S-box in MPC. So it's not specific to Skinny's 4-bit S-box, but you can use any 4-bit S-box. We also show that you cannot do the same approach to improve the 8-bit S-boxes. You can apply it, but it will be slower and cost more multiplications than doing the Boolean circuit. In the paper, we also have a benchmark and implementation of the SKINNY that I already showed you. For the SKINNY 128.256, this is the SKINNY instance that uses an 8-bit SBox, and there we cannot report an improvement. And then for Photon P100, this is the smaller instance of Photon, which uses a 4-bit SBox, so we can apply the same techniques and we get roughly the same speedup. And for Photon P256, this uses the AES SBox, and there we can apply the non-AES optimizations from the literature, and we get also a speedup here compared to the Boolean circuits. And then I want to highlight again that this is not limited to SKINNY or Photon, but it can apply to any ciphers that use 4-bit SBoxes, like these and many more. Okay, that's it from my side. The ePrint will hopefully appear by the time the conference is, and the data and the code is available online. Thank you. Then I'm ready for questions.